In our usual pattern for introducing the subject and then working with the subject, this is the segment where we're going to write some code using structs and pointers to structs and pass them around. So a couple of specifications, and most of this segment will be spent typing in the development environment. Get your development environment running at the same time, so this is not just a passive exercise. You have to be participating in this, and it will help you to understand it if you type the code along with me, solving these problems using structs. Okay, here's our first spec in this problem-solving segment, and you might notice that we haven't been in the development environment in the last couple of segments. I did this on purpose. I don't think that you need to see me actually type things as much as you did in the beginning of the course. If that's still kind of a problem, if you weren't typing along because I wasn't typing, then you should have been, but we'll start typing in this one as we solve these problems. So here's our first spec. We're going to make a struct that represents time in hours, minutes, and seconds. And we have two functions to write to play with that struct. One of them is going to just output the time in a standard format, HHMMSS, with colons in between. And then we're going to write a function that takes a pointer to a time struct and will normalize the data. So the first one could have been solved by a pass by reference or a pass by value, and maybe when we're playing with it in the code we'll solve it both ways to show you the difference. And the second one needs to be a pass by reference, so that function needs to pass a pointer so that the function can actually change the time object and have the changes persistent or passed back to the calling function. So let's go into the development environment now and start playing with this defining of structs and passing them around to functions. So here we are in Visual Studio again, and I have started an empty project called Time Demo, and I copied the comments of what we're going to do from the PowerPoint slide. So we're going to make a struct that represents time with hours, minutes, and seconds, and then we're going to pass that around to functions and just kind of play with it and make sure that everybody feels comfortable with making these structs. So I'm going to define the struct here before the main. When you define your new data types or do things like pound define or pound include, the things that are, these things should come before the main so that they have file scope. That means that they're available throughout the entire .c file that we're working in. So let's put our type def here, and we have a new data type that we can now work with. And just play with it, since we haven't made any of these in the development environment, and that might make you uncomfortable. We're going to declare a variable of our new data type, and I'm going to call it noon, which is a time. And then I'll say noon dot, and you see that it pops up the things that we can choose from. The component parts of this data type are hours, minutes, and seconds. So noon hours is going to be 12, and minutes, I don't want to put 0 in all of these, so maybe I should have called this variable noon 30, just so that we have something to look at. We'll put 12, 30, and 0. Let's just go with that and see what happens. I'm going to put a breakpoint there so that we can see what's going on in the debugger. The debugger will help us understand what's going on, and we should always be asking it. It's free, to ask the debugger to show us what's going on. So I'm going to compile this so that we can look at our new variable noon in the debug window. And there we've hit the breakpoint, and in our variables window it's valuable. If you click on locals, you can see the variables that are available inside the function, the local variables. So we can pop this open. Noon has 12 hours, 30 minutes, and seconds is this big ugly number because the arrow points at the line of code that we have not yet executed. And look at the data type for our variable noon. It already knows that we have a data type called time, and all uppercase is my convention for something that has been type defed. So let's execute that line of code and make sure that we can see in the debugger that everything is the way that we expect it to be. Remember that executing one line of code is a step over, And now we have valid values in the 3 component parts of our variable called noon, and I decided it should be 12:30. I'm not sure why. So let's start making functions that work with this new data type. And our first spec says we're going to write a function that takes a pointer to time that outputs the time in the format HMMSS. Well, I'm going to start out by not doing what the spec says. I'm going to, instead of passing a pointer to a struct, why don't we just pass in a time object? This function doesn't have to return anything, so we'll make it a void, and let's make it called print time, and I'm going to say that it takes a time t. I think will be okay. So this is a function prototype. In a function prototype, you don't have to put variable values. So time or time t, if you put variable values there, it doesn't hurt anything, it just doesn't do anything either. So let's make this function definition. I'll make it right here so you can see the struct and the function prototype, and then maybe I'll paste it down below after we're done making it. So here's the function definition. It takes a time, and I'm going to call it t because I'm a little bit lazy. You probably shouldn't be using 1-letter variable names. I will frown at you if you use 1-letter variable names. And our objective now inside of this function is to print it out in some standard format. So let's do a printf of the hours first, and we're going to say %2i, and then we're going to put a colon, and we'll put %2i for the minutes, and a colon, and %2i for the seconds, and a carriage return. That will be okay. We'll put it on its own line so that we can see what's going on. So now we need to get out the component parts of that thing t, and we can say t dot hours, t dot minutes, and t dot seconds. You can get comfortable with the Visual Studio helping you to type these things. And let's call this function passing in the time object that we created there called noon. So I'm going to call print time, and I'm going to pass noon. And you see that the data type of noon is a time object, and the print time method is expecting a time object to be passed in. So let's compile and run that. It will hit that breakpoint. We'll probably just continue when it hits the breakpoint and see what happens. If it doesn't do exactly what we want, then we'll go back and start playing with it. So I'm just going to hit F5 to continue from here and see what it does. Well, it does almost what we want. There should be 2 digits printed out in all cases. So this, if we had only 5 minutes here, it would have only printed out 1 digit. And you can see that because we have 0 seconds here, it hasn't printed out 00, which is what we would like in a standard representation of time. So I'm not sure if you'll remember this or not. If we put 02 before an I, that's a format specifier that says that we should have, if we put 02 before the I, it's an indicator that we want leading zeros, and we do want two digits printed out, even if the number is less than 10. We want 2 places taken up so that the time would appear the way that you would expect it to in a standard representation. Well, you know what I mean by that. So let's run this one in the debugger, and we will step into the function called print time. So we've hit the breakpoint there, and remember that we have this variable called noon of time type, and we're going to step into this function called print time, stepping into. So now we're about to do this printf. So let's make sure that we still have what we expect. We have an object of type time, and it has the values in it that we expect, the 12, 30, and 0. And now we're going to output it using this new format specifier. So I'll execute that line, and we will see if it did what we expected. And that's good. It output the 2 digits here because of the format specifier that forces not only a width of 2 in the output, but leading zeros if there aren't 2 digits to be printed. Okay, so now let's go back to the spec that said we should pass a pointer to a struct. So this was a pass by value, and we want to make a function that does a pass by reference. So let's make another one. We're going to call it print time, and I'll put reference in the name of the function so that we distinguish them. And what will the data type of the parameter be? A time pointer. And I'll put the definition of the function right here so it won't get away. We'll be able to see what we're doing. Time pointer. How about p time? And we're going to do the same thing. We're going to output the time, but this time, instead of outputting the time, we can use the same format specifier. But p time, we don't want to use the dot operator here. We're going to use this operator. And you see that Visual Studio tells you what you have available when you use the dot operator. So the same thing, hours and minutes, and p time, seconds. And what we're demonstrating here is if you have a pointer to a struct, so p time is not a struct, it's an address, then we use this right arrow operator to get the component parts out. And let's call our function now. We're going to call print time reference, and instead of passing in noon, we're going to pass in the address of noon, which is a pointer to a time. I'm probably not going to run that. It's a little bit too simple. I'll let you do it. It takes up quite a bit of time in these videos. But what I would do here is, while we have a time pointer, make the point explicit that p time is a pointer to a time, and we could dereference that, and then from the dereferenced pointer go and get the component parts. And the reason that we don't do this, it works exactly the same as this right arrow. The only reason we don't do this is because it's just too awkward. So it's very common that people will pass around pointers to structs, and dereferencing and then getting the component parts out is kind of awkward, and it makes you think at another layer of complexity. So we're going to use this dereference operator instead. Now, what happens if I change the hours in here? Suppose inside of this function I change the hours to 11. Would that change the object? And let's do p time using the right arrow operator. Let's change the minutes to 15 minutes. Now, this is one that I want you to see in the debugger. So when we pass an object by reference, meaning we pass the address of the object into a function, that function could possibly change the object, and that change would come back to the caller. And when we pass it by value, the way we did here, suppose in the function where we passed by value we said t.hours gets, I don't know anything. These changes would actually do nothing at all to the object that was passed in. So a pass by value is information coming into the function only. The function cannot change it. That's because this function has its own copy of the time object. Manipulating its own copy doesn't change the copy that we actually had declared in the main. But this is a different story. This function can change the component parts of the object that was passed in. So this is one that's important, and I want us to actually see this one happen. So let's compile and run to the breakpoint, and we will call the print time function that's a pass by value, and then the print time function, print time reference, and see that the first one could not change the object, but the second one did. So I'm going to step into this function, the print time function, and we'll execute some lines of code here. First of all, it outputs the time onto the screen, onto the console, and then we're going to manipulate the object that we have called t, set the hours to 23 and the minutes to 39, and you can see down here that we have actually changed the time object that was passed in to 23:39:0. And when we get back to the main, the object that we were working with in main has not changed. So this is proving that this is passing information into the function only. Information is not coming back out, and that's a pass-by value. And now we have this other function that passes in the address of the struct, and we're going to step in and output the time. Exactly the same thing happened as before, and this time when we change what's pointed at by p time, we changed it to 11:15, and we're changing the actual object that we had declared in the main. So when we go back to the main this time, our noon object now has been changed to 11:15. So there's the difference, a pass-by value and a pass-by reference. So our next spec is to write a function that takes a pointer to a time and normalizes the data so that there are fewer than 60 seconds and fewer than 60 minutes. So let's go and make the prototype for a function called Normalize time, and it's going to take a time pointer. So here's the function definition. It's not going to return anything. It's going to be called Normalize time, and it's going to take a time pointer. I'm going to call it t. So what is our job here? We don't want there to be more than 60 seconds, so a time that's expressed that has more than 60 seconds seems to be kind of a strange way of representing a time, so we have to get rid of any extra minutes that are stored in the seconds field. So let's take the extra minutes out. So I'm going to declare a variable called extra minutes, and then we're going to say extra minutes gets t's seconds divided by 60. So that's an integer division. Suppose someone passed in a time object with 80 seconds. 80 divided by 60 is 1, and we have some extra minutes, or at least one extra minute stored in the seconds field. If they passed in 120 seconds, then we would have 2 extra minutes, and extra minutes would be 2. So now let's take t's minutes field and add to it the extra minutes. Now we want to take, if there are any extra hours in the minutes field, and we have the same issue, extra hours. Suppose someone passed in 70 minutes. We would want that to be 1 hour and 10 minutes. So we'll say extra hours is t's minutes divided by 60. So we're taking out the number of hours that there are, and t's hours we're going to add in if there are any extra hours. And apparently in this specification the number of hours can be as many as you want. So there could be 1,000 hours in this time. And there's a bug with it. There's a bug in this. Do you see it? Are we done? Sometimes it's hard to see the bugs. Let's make another time object. So we're going to use this time to test our function for normalizing. And we're going to say, let's initialize this struct. I'm not sure that we've looked at that before. We can use an initializer that looks like an array initializer. So I'm going to put 1 hour, 70 minutes, and 130 seconds. So that is not a time in a normalized representation of time. We wouldn't say that we have 130 seconds. We would, in a time, we would say that we have less than 60 seconds, and we would want more minutes. So let's go now and call the normalize time and pass in an address of that. The address of that test. Print time method is going to have a strange way of dealing with 130 seconds because print time forces the number of seconds to be represented in 2 places of output. So if we normalize it and then print it again, so we're going after a bug here. I've written a function to normalize the time, and we're giving it this time 170, 130, and let's stop at the breakpoint here and see if we can walk through this function and find out what the problem is. Okay, well, I have a compile error. Happens to all of us. Unresolved external symbol normalized time. Okay, so what have I done? Oh, I spelled it wrong. It's a less embarrassing syntax error than it could have been. So we're going to run to the breakpoint and make sure that we can see everything that's going on. So we have an object called test of type time that has 170, 130 in it. So our initializer has worked. And now we're going to step into the function normalize time. And our objective is to make sure that the number of seconds is less than 60. So we have an object in here called t, and it has 130 in the seconds field. So 130 divided by 60 in integer arithmetic should be 2. So we have, and now we're going to add those 2 minutes onto the minutes, so we should wind up with 72 minutes. So let's step over that one, and that's correct. So we took the 120 seconds out of the seconds field and we added it into the minutes. Now we're going to take every 60 minutes, we're going to add 1 hour to the hours field, and we should wind up with, in hours, 2 hours. And what's happened here? Is this correct? No. When we took the 120 seconds out and added 2 more minutes to the minutes field, we didn't reduce the number of seconds. So we have to go back and do that now. I'm kind of hoping that everyone saw that bug, but I'm not sure that you did. Okay, so now when we increase the number of minutes, we need to also decrease the number of seconds. So t's seconds minus gets, well, how should we do this? We could take the number of minutes, multiply it by the number of extra minutes, multiply it by 60 and subtract that from seconds, or we could just take out, using the modulus operator, take out the 60s. Do you see how that's working? 130 modulus 60 is going to be 10, which is the same thing as subtracting 120. And when we move the extra minutes into the hours field, we should be saying, let's reduce the number of hours by the same thing. Modulus gets 60. Let's just run this. Well, we'll print out the time, and then we'll call the normalize function, and then we will print out the revised time. Okay, here's the time that's not normalized, 1 hour, 70 minutes, and 130 seconds. And then I'm going to just step over the normalized time because I believe that it's working. If it's not, then we'll go back. And now let's print out the new time object. So we have 10 seconds, and we added 2 minutes, and when we, well, this is not right. The minutes should have been reduced by 60 minutes to add 1 hour. Well, darn, there's a bug. Okay, yes, it's t's minutes modulus gets 60 that we should have put here. I hope you're doing this along with me, and I hope you're appreciating that it's very easy to make mistakes when you're programming, and it's even easier to make mistakes when you're talking and typing at the same time. So a complete focus on what you're doing, which is not what I'm doing right now as I explain this. That's my excuse for typing that bug. Okay, I'm just going to execute that method believing that it's going to work this time, and we'll go out and see if it did. Okay, so this time was normalized into 10 seconds, so we took 120 seconds and added 2 minutes over here, so we had 72, but we took 60 of them and made it 2 hours. So this is a normalized representation of this time. Very good. Let's go back and look at the code. I'll just kill this debugger. We could have made this maybe a little shorter. We didn't need to store the extra minutes. We could have just added this value into the minutes and not stored it as a local variable, but I wanted to do this in more steps. Sometimes it makes sense to write the code in a fairly long, inefficient way, and then when you're comfortable that you have the right solution, then shorten the code. It's very much like writing an essay and then going back and rewriting it so that you have a better solution. There was a famous programmer who said there's no such thing as writing good code, there's only rewriting good code. I tend to agree. Let's go back to the PowerPoint slides and look at another spec. Okay, here's the second spec that we're going to work on, and it gets a little more challenging each time, as you would expect. So we're going to create an inventory system for a hardware store, and we're going to say that these products that we have in inventory, each one will have a name and a product number, a wholesale price, a retail price, and the number currently on hand. So our job working for this hardware store is to help them keep track of their inventory, and the beginning step is to define the data structure that represents one product. And then we're going to make an array of these objects that represent all of the items in a store. And you can see down the road that we would have a more elaborate inventory system where you could add things to inventory and delete things from inventory. So there's the first part of the spec. We're going to create the struct, and we're going to make an array of them. Then we're going to write a function that fills in some of the array with some data. We'll just make it up, some hammers that cost $5 or something. And we will maintain the effective size of the array. So as we add things into an array, we will maintain how many things we have added. Then we'll write a function that outputs a table of the products on hand. So this is kind of an inventory report, and we will write a function that generates a report of all of the items that we have fewer of. So this is a start for how you might imagine a hardware store would want to use an inventory system. Which things are we low on? And we start to see that there's a business objective here. Just the very beginning of it. So let's go to the development environment, and I'll take some of this with me as we develop this project, and we'll work with making a more realistic system that uses structs. Okay, so here we are starting a new project. I'm calling this one inventory. I guess I called the project products, and I called the C file inventory. So remember what our objective is. We're going to create a struct that represents one product, and we have this specification that it has a name, and it has a product number, a wholesale price, a retail price, and the number currently on hand. So this struct starts to be more interesting than the last ones. So let's do a type def of our new struct, and it will be inside of these braces, and we're going to call it product. And my convention for this type of a struct is to use all uppercase in the name of the new data type. So let's go back. Each product has a name. So what data type will we use? A product has a name. Let's use a character array called name, and we're going to put something in there that has enough space for the name of any product. So let's say we're going to reserve enough space for 40 characters there, and it has a product number. What data type should that be? How about a short int? So that's a 16-bit data type. If we've got a lot of these, then maybe a short int would be better than a long int. I'm not sure. So a wholesale price, a retail price, and the number currently on hand. The wholesale price and the retail price, let's make those doubles. So we could probably calculate how much profit we make on each of these things if we subtract the wholesale from the retail. And on hand, probably a short int again. So there's our data structure. And let's make one of these things. Let's say product hammer. So it's a hardware store. We have a hammer. We're going to initialize it to the name is going to have in it hammer, and the product number char the wholesale price of a hammer, let's suppose we get these wholesale for $5.50 and we sell them for $8.99, and on hand we have 4 hammers. Okay, so the first part of the spec is done, that we have a struct that can represent the things that we have, the products that we have in our hardware store. Now it says let's make an array of them. Make an array of objects that represents the items in the store. So what is the data type of the array? I'm going to call this array our inventory, and I'm going to allocate a whole lot of space for it. So let's suppose we sell 500 or a maximum of 500 different products in our store. So now we have an array of these product things, and inventory sub 0. What is the data type of inventory sub 0? It's a product, and inventory sub 1 is a product, and each of those elements in the array has all of these characteristics. Okay, so far it's not very difficult, I think. Let's go and get the next part of the spec. So the next item in the spec was to write a function that fills in some test data in our array and put in at least 5 items and maintain the effective size of the array. I'm going to throw away this comment just because we don't have much room here on the screen as we're recording things. I need you to be able to see as much as possible. So we're going to write a function that fills in some test data into the array. So we've got this big array of inventory, and we want to fill some of it in and maintain the effective size of the array. So what do we mean by the effective size? The size of this array is 500, but it doesn't have anything in it yet. So as we put stuff in it, we should keep track of how many items we have in this array. So I'm going to declare another variable here called the effective size. So the size of the array is 500, but the effective size is how many items are actually in there. And we're going to make a method that just fills in some data in the array. This is not a very realistic method, not a very realistic function for our inventory system. It's just a demonstration of using an array of structs. So I'm going to make a method that doesn't return anything, and it's called fill in products, and I'm going to pass in an array of products. A product array is the data type of the first parameter, and I'm making the function prototype here. And I also want to pass in the effective size of the array, but I want the function to change the variable effective size. So should I use a pass by value or a pass by reference? I'm going to pass in the address of the size, the effective size of the array, and I'll call it p size, a pointer to size. So that's the function prototype. Now let's make the function definition. So I'm passing in the array of products, and I'm passing in an int pointer, the effective size of the array. And before I even start implementing any of this, let's see if we can get this to compile. We're going to call the function fill in products, and we want to pass in the inventory. That's that big data structure that we've created with 500 elements, and we want to pass in the effective size of the array. So let's initialize effective size to 0 here because we don't have any objects yet. So here's what's going on. We're passing in the array of products, and we're passing in the effective size, and each time in here we add something to the inventory array, we're going to increase the effective size of the array. Okay, so let's just start by saying inventory sub what? Well, let's say sub p size. So we passed in a 0. If we passed in a 0, that means we're accessing the 0th one. What does inventory.psize have? Look, it has a name, and we want to assign that to something. I'm going to make a mistake here intentionally. So we have a handsaw. Now let's start adding the other characteristics of the handsaw. Its product number, we'll just make something up, is 3456, and its the number on hand. We've got 12 of those, and the wholesale price is $12.34, and the retail price is $23.99. Retail prices always end in 99, don't they? Okay, so we have one new object added to our array, our inventory, and that means that we should increase the effective size of the array. So we're going to take star p size and increment it by 1. Okay, there are 2 bugs in this code, and these are very common bugs in C programming, and they're hard to find. The first one is up here. What it looks like is we tried to move an array of characters by an assignment statement, and you can't do that. How do you move an array of characters or a string? Let's do strcpy, and the destination is the name, and the source is this string that we've hard-coded here in quotes, a handsaw. So that's one bug. Anytime you assign a string to a car pointer, it's wrong. You have to use string copy. So let's go back up here. Now that we know that we're going to need the functions from the standard library string, we'll include string.h here. Okay, well, we haven't compiled and run this for a long time, so I'm not sure that it's working. So let's put a breakpoint here and optimistically ask for it to run, and I'll show you the other bug as we execute this in the debugger. Okay, we have a build error. Let's go and have a look at what the compiler errors are. Okay, we have an unresolved external fill-in products, and of course it's a spelling error again. Okay, that was the last of the compile errors, so we'll run to the breakpoint and we'll have a look in the debugger at the things that we have created, including this fill-in products function. Okay, so we've hit the breakpoint. Let's look in the debug window. Before we step into the function, just look at what we have here. We have an inventory array, and each element in this array is going to be a product. And if we look in inventory, let's pop open the 0th one. So the 0th element in the array has name, number, wholesale, retail, and on hand, and there's junk in all of these. So our objective with the fill-in products is to go and look at, fill in some information, and we want the effective size of the array to also be updated while we're doing that. So notice that the effective size of the array so far is 0. That means we haven't put anything in the array so far, so that's making sense. Let's step into the function. Remember, there's a bug in here somewhere. So inside of this function we have the array of products called inventory, and we've passed in the pointer to the effective size. So let's have a look at inventory, and we have what's pointed at by p size is 0. So we're saying at inventory sub 0 dot name is where we're going to copy the string handsaw, and let's execute that. And the name here is handsaw, and then we start filling in the other parts, which are not so difficult. I probably should have done them in the order. Now let's watch what happens here. We want to make the effective size of the array 1 because we've now filled in one object into the products array. And when we step over this, something strange has happened. We wanted to go from 0 to 1, and now we've gone to negative 85 billion or whatever that number is. So this statement is wrong. What's pointed at by p size plus plus, you might remember that we used a statement similar to this in the section on manipulating arrays with pointers. And the problem here is we have incremented. The increment operator grabs onto one thing on its left. we have incremented the pointer instead of incrementing what's pointed at by the pointer. So this is an int. That's what we wanted to add 1 to, but in fact we added 1 to the pointer. This is a very common bug. I left it in there on purpose because it's just so common and it's fairly painful to find. So I'm going to kill the debugger here, and I'm going to show you that we can force the dereference to happen. So what the increment operator now grabs onto is the dereferenced int. So we're adding 1 to the dereferenced int pointer. We're adding 1 to the int now, and the effective size when we come back from this function will be incremented. So 2 very common bugs demonstrated in this function. Trying to assign an array of characters instead of doing a string copy, and incrementing something that was passed by reference. Make sure that you do the dereference first and then increment the variable as opposed to incrementing the pointer by mistake. So now if we step into the function, we're doing the same thing that we did before. We're filling in the 0th element of the array, and when we come back from that function, the effective size of the array is now 1, and we can look at inventory sub 0 is a handsaw with this other product information. So I'm not going to complete the whole spec here. The spec said add at least 5 items to that array of inventory, and it would take too much video time since you can make up some products that would be for sale in a hardware store. So let's go back to the spec now and get another task to add to this inventory project. Okay, so our next job in this project is to create a function that outputs a table of the products on hand. So we have 1 product on hand so far. We have some handsaws, and we're going to write a function that will create an inventory report. The inventory report will take the array of products and the effective size of the array. You remember that the function prototype doesn't require names there. And here's the function definition. So I'm going to say inventory report. It takes an array of things called of type product, and it takes the effective size of the array. And our job in this one is really quite simple. We're going to make a for loop that will loop over the items that we have in inventory. So we're going to loop over the items that we have in inventory, and each line in the report will be 1 inventory item. So let's, before we start the loop, let's put a header on our report. How's that? Inventory report. And let's make it nice and underline it. If I had time, I would center it on the page. So our inventory report, also a little more headers. We're going to say, here's the product name, product number on hand. That's how many we have in inventory. And the wholesale price and the retail price. And do we want to underline that one too? You can probably do a much better job of this than I can. I'm not very neat. So we want to loop how many times? We're going to loop over the available items in inventory. So let's say int I gets 0 and I is less than the effective size. So each time through this loop we'll be looking at the ith item in inventory, which will be the next one. So let's put 1 line on our report, and the percent formatter, the percent sequence formatter for a string is %s. And what would the width of the name be? How many characters do we want on our report for the name of the product? Let's try, that doesn't sound like enough. Let's try 10 for the name and then the product number. Let's put 10 and then the number on hand. What is the data type of the product number? It's an integer, and then the number on hand is also an integer. Let's put it in 10 spaces and we can fix it up later. And the wholesale price and the retail price are both doubles. So let's say percent, a width of 10, 2 places past the decimal, and a width of 10 with 2 places past the decimal, and that's one line on our report. And now we need to put the items. So inventory is our array, and we're going to take the ith one, and we'll say the name, and then inventory sub I, the product number, inventory sub I on hand, the wholesale price, and the retail price. And this is probably going to look very messy, and we will have to go back and figure it out. Are there any compile errors, do you see? Let's go and call inventory report and pass in this very small inventory that we have so far. So inventory report, and we're going to pass in our inventory. I think we have a handsaw, and we're going to pass in the effective size of the array, which I think is 1 after we filled it in. So let's run this, assuming that there are no syntax errors, and see if we have made an inventory report. Even though it's not very interesting, it will only have one thing on it. Oh, whole bunch of syntax errors. Good. What have we done here? The way to find the syntax errors is to just double click on the error message, and my double clicking doesn't work when I'm recording. I'm not completely sure why, but we have an error on line 26, actually a whole bunch of them. Is anyone seeing it yet? Oh, you cannot declare the variable inside of the for loop in C. That's something that's commonly done in Java and in C++. You cannot do that in C. Okay, we ran to the breakpoint, and let's believe that the method that we wrote before is still working. So fill in products, and now we should have 1 product in our inventory. So our effective size is 1. We have 1 product in our inventory, so our effective size is 1, and now we're going to step into the report function that we just made and see if, well, we'll print the heading to the report, and now we're going to output 1 line of information on the inventory report. There should only be 1. That's good. So we stepped through this loop 1 time, and let's see how big of a mess we made. Well, we got handsaw right. Maybe left justified would have been better. The product number, the on hand, I think we had 12, but now we've got some problems in here. So we have some bugs in our printf statement. Percent 10.2. I wonder if I forgot to put the LF on that one. Okay. So you're getting the idea of making a report from an array of structs, and we're starting to get a feel for a real business purpose for creating these structs and passing them around. And the next thing after this will probably be, could we write them in a file or put them in a database so that the company's inventory can't be something that you type in or hard code in your program. Obviously it has to be something that would be useful to the company to update and maintain their inventory records, and then go and search for things like, what are we low on, what do we have too many of, what is the value of the entire inventory right now, and so on. So there was one more spec in this problem, the inventory problem, that said go and look for the items in inventory that were low on. And low, I think, was defined as fewer than 5. And I'm going to leave that function as an exercise to you, because there is really nothing new in that function that we haven't demonstrated in the functions for filling in the products and generating an inventory report. It will be an exercise for the reader. Well, what I hope is happening is that this segment is pulling it all together, the things that we've learned in the last couple of segments. And this might be the time where you want to go back and watch the first segment on structs again so that you would have a solid understanding. If you weren't ready to hear what was in the first segment on structs, then hopefully you're ready to hear it now and you'll hear more things. That's just kind of how the way learning this stuff goes. In this segment we also learned that structs should be used to represent one thing. If you design your struct so that you just throw a bunch of stuff in it that's kind of unrelated, then you don't have a good name for it. If it's easy for you to think of what the name of the struct should be, then it's probably a good design that struct represents one thing. Multiple instances of a struct can be stored in an array, and an array of structs works exactly the same as an array of primitive data types, and you can use pointer offset syntax to manipulate an array of structs. Everything works exactly the same way as it did in arrays of primitives. It's a common error when people are designing structs that they will put a car pointer in their struct as opposed to an array of characters. You have to be very careful with this, because when you allocate space for a struct, if you've only allocated enough space for the pointer, where are the characters going to go? So if you want a string in your struct, which is a pretty common thing to do, the name of the customer, for example, then you don't want just a car pointer in there. You want to make sure that there is enough room to store the name of the customer. That's a very common problem when people start working with structs, and the code runs, but it does strange things, and it's quite frustrating. So watch for that problem. And I've said this before, probably more times than you want to hear, but draw a picture of the data that you're working with. So if you have a struct, draw a picture of it. If you have an array of structs, draw a picture. Use arrows to indicate where the pointers are going, and then look at your code and make sure that it's matching the picture. That's my best tip for not being frustrated when you're working with structs and pointers to structs and arrays of structs. See you in the next segment.